Hello there, welcome to the Learning of Engineering tutorial video lecture. In this video lecture, we are trying to learn the effect of internal diameter on the dimensions of a thin cylindrical shell. It means we are dealing with the thin cylindrical vessels. As we know, it has the internal diameter and outer diameter, and it is used to store the fluid under certain pressure conditions, and due to this reason, it is going to be exerting the pressure on the walls. So on that basis, we have derived the circumferential stress, longitudinal stress, and the maximum stress is going to be acting, and efficiency of the joints we have considered. Now in this case, we need to find out if the internal member, that means internal diameter, is going to be subjected to the pressures of the fluid, then how the dimensions are going to be changed. As we know, the change in dimensions we generally used to measure in terms of the strain. There we can see this is going to be the circumferential forces are going to be acting in the transverse direction, and longitudinal stresses are going to be acting in the longitudinal axis. That is, the sigma 1 is going to be your circumferential stress, sigma 2 is going to be your longitudinal stress. We know these are going to be stresses are developing inside the material. These materials are going to be showing some resistance force, that's why the stresses are going to be building. It's not only the stresses, at the same time the strains also going to be developing. These are the consequence of one after one. So there we can see the strain also in the circumferential direction and longitudinal directions we are going to be considering. There we can see here the epsilon 1 I have taken, that's indicating the circumferential strain, that means which is acting in the transverse direction, and longitudinal strain which is acting in the longitudinal direction. So this strain we need to define in terms of the stress and Young's modulus, and that we are equating to the change in dimensions of the component. So as we know, this member is subjected to the two stresses, then how could you write the circumferential strain? So that's going to be epsilon 1 is equal to, what is the formula we have? That's going to be epsilon 1 is equal to, we know the Young's modulus is equal to the stress by strain we are going to be taking. Now I am going to be removing this strain over here from the denominator. I will write sigma by, that means stress by Young's modulus. So here I am going to be writing sigma 1 by E, because we are going to be taking in the transverse direction. At the same time, the longitudinal direction also load is acting. It means that we need to be taking the Poisson's ratio, that I am going to be writing mu into sigma 2 by E. So that means, can you see here, the strain is going to be developing not only because of the sigma 1, at the same time sigma 2 also going to be acting over here. So that's why we are getting the final strain in the direction of the circumferential direction. At the same time, there we can see the dimensions also going to be changed in this case. So then how the dimensions are going to be changing? So that's going to be epsilon 1 is equal to change in dimensions divided by original dimension. Original dimensions of the system. So in this case, which we need to be take it? So that's going to be here, we need to take it the circumferential. Change in dimensions means here we are going to be writing the final change in dimensions minus original dimensions, then only we will get the change in dimensions. So that I am going to be taking over here. So this equation we are writing sigma 1 is equal to del D by D I am going to be writing. So the del D is nothing but the final diameter of the component minus initial diameter of the component. This is going to be the initial diameter. So then how could you find out the final dimensions? So now I am going to be writing those dimensions of the component. Here we can see this I am going to be writing the circumferential diameter, that's going to be pi into D plus del D we are getting, minus pi D is going to be your circumferential, that's going to be pi D I am going to be considering. So from this one, pi D going to be cancelled here, and here also pi is there. Finally I am going to be getting the dimensions of the component is going to be, the strain is nothing but your del D by D we are getting. So if I am going to simplifying this one, pi D, here is the positive and here is the negative, both are going to be cancelled out. and here is the pi d is going to be there, pi del d by del d. So then del d by d we are getting. Now what I am going to do, I am going to be equating this one as well as these equations. So epsilon is equal to del d by d, I got it. So I am going to be equating these two, then I will find the strain in terms of the pressure and the diameter of the component. So if I start to simplifying this equation, epsilon 1 is equal to Pd by 2Te, I got it, minus mu into Pd by, this is going to be 4Te, I am getting. So this is the equation. Common terminology, suppose if I am going to be taking out Pd by 2Te, if I am taking Pd by 2Te, that I am going to be writing 1 minus 1 mu by 2 we are getting, and I am going to be equating here. So that is equal to del d by d is equal to Pd by 2Te 1 minus mu by 2. So from this equation we can calculate the change in dimensions of the component, that's going to be del d, easily we can calculate it. So similarly the same process we are applying for the longitudinal strain also. Now we need to find out the longitudinal strain. How to find out the longitudinal strain? It means that the longitudinal strain I am defining in terms of the stress Young's modulus and dimensions of the component. So there we can see epsilon 2 I am going to be writing now. Now we need to take in the second direction, that is the longitudinal, that I am writing here sigma 2 by E minus mu into sigma 1 by E I am going to be writing, right? And if I am going to be substituting sigma 1 as well as the sigma 2 values in this equation, that's going to be epsilon 2 is equal to Pd by 4Te minus Pd by 2Te I am getting. Then I am going to be taking some common terminologies. Epsilon 2 is equal to Pd by 2Te. This is going to be, here is the mu we are getting, 1 by 2 minus mu. So this is the strain we can calculate. Now I am going to be comparing with the dimensions of the component. That's epsilon 2 is equal to del L by L. That's going to be change in length by original length. This change in length I am going to be getting the final length of the component by initial length of the component by initial length of the component. So that I am going to be equating the sigma 2 as well as these equations, that I am going to be getting del L by L Pd by 2Te 1 by 2 minus mu we are getting. So this is the way we are going to be calculating the dimensions, that means the circumferential strain as well as the longitudinal strain of the component. This is generally we are applying for the two-dimensional component. Suppose volumetrically how much strains are going to be coming, that we will see in the next video lecture. So I hope you are able to understand the concept of how this internal diameter is affecting the dimensions of the component. Why? Because internal diameter is going to be, the force is going to be acting. That means the fluid pressure is going to be acting internal diameter, and that is started to transforming the load to the different parts of the member. Then automatically the dimensions also going to be affected. So that's to identifying the dimensional changes, that we have taken circumferential strain and longitudinal strain. I hope you are able to understand how to develop the mathematical model in order to understand or to assess the response of the system when the loads are going to be acting in terms of the strain. So still if you feel any difficulty regarding the understanding these concepts, so please put in the comment section so that I can reach you out. Thank you.